All right, let's dive into a question that seems super simple on the surface, but ends up challenging how we see, well, everything. We're going to talk about the physics of relative motion. So, let me just ask you, right now, wherever you are you sitting still? I mean, it probably feels like it, right? You're not running, you're not in a car, you feel stationary.
Well, I'm here to tell you that feeling of stillness, it's a complete illusion. Because right this second, you are whipping through the cosmos at a speed that is just mind-boggling.
As our little planet makes its yearly trip around the sun, it's dragging you along for the ride at an incredible 107,000 kilometers per hour. And nope, that is not a typo.
Let me put that another way for you. That's about 18.6 miles every single second. So yeah, even though you feel perfectly still, you're actually on the cosmic roller coaster of a lifetime.
So this brings up a really interesting puzzle, right? If absolutely everything is constantly moving, planets, stars, you, me, people on a train, how in the world can physicists possibly measure any of it with any accuracy?
Well, the secret is all about finding an anchor point. And here's the catch. We're not looking for some absolute fixed spot in the universe, because, spoiler alert, that doesn't exist. We just need a temporary one that we can all agree on.
In the world of physics, this anchor is called a reference frame. You could think of it as the background, or the coordinate system, that we decide to use to measure an object's motion against.
But let's just cut through the jargon. All a reference frame really does is force us to ask the single most important question when we talk about motion. Moving relative to what? Because the answer to that one little question changes absolutely everything.
Just look at what this means for you, right now. If your reference frame is the ground under your feet, your velocity is 0. You're not moving. But if we change our reference frame to the sun, suddenly you're blasting along at 107,000 kilometers per hour. Same person, same moment in time, but two wildly different velocities. And here's the key. Both of them are 100% correct.
Okay, so to really play with these ideas, we need to be on the same page. We need a shared language. Just a few key terms that help us talk about what's going on inside these reference frames.
It's pretty simple, really. First, you've got displacement. That's just a fancy word for a change in position. Then, there's velocity. That's just speed, but with a direction attached. And finally, acceleration, which is just any change in that velocity. That's it.
So, to a physicist, this isn't just an incredibly determined-looking honey badger. Nope, it's a honey badger with a very specific position, displacement, and velocity, all measured relative to the ground. See, we can describe any moving object this way.
So, what do we do with all this? This is where it gets really, really cool. What happens when you've got motion happening inside of another moving system, like say you're walking down the aisle of a moving train? How do we put those two different worlds together?
The rule for this is actually beautifully simple. You just add the velocities together. An object's total motion, relative to the outside world, is its own motion plus the motion of the world it's inside of. And this little equation is the key to it all. The velocity of a person relative to the Earth, let's call it VPE, is equal to their velocity relative to the train, VPT, plus the train's velocity relative to the Earth, VTE. The trick is making sure those inner labels, T for train, match up. That's how you link the different frames.
You can actually see it right here. These arrows are what we call vectors. They show us both the speed and the direction of motion. So if the train's vector is, say, 10 meters per second heading east, and you decide to walk the other way at 2 meters per second, your smaller vector basically subtracts from the train's. Your final velocity relative to the ground is just 8 meters per second to the east.
Okay, so that was all in a straight line. But what about in 2 dimensions? Let's picture this. A car is heading due east at 80 kilometers per hour. At the same time, a truck is going due south at 70. If you're sitting in the driver's seat of that truck, what does the car's motion look like to you?
We use the exact same rule, just add the vectors. We need the car's velocity relative to the Earth plus the Earth's velocity relative to the truck. Now hang on, think about that last part. If the truck is moving south from the Earth's point of view, then from the truck's point of view, the Earth has to be moving north. We just flip the direction of that vector.
So now we just add our 2 vectors, the car's eastward motion and the Earth's northward motion from the truck's reference frame. When you combine those two at a right angle, you get a new diagonal path.
A quick bit of math shows that from the truck's perspective, that car looks like it's speeding away at 106 kilometers per hour in a direction that's kind of northeast.
Phew. Okay, so after all of that, what's the one big idea you should walk away with? It really all comes back to that very first question we asked.
Here it is. There is no such thing as absolute motion. There is no such thing as absolute still. Every single measurement of movement is totally meaningless until you define your reference frame, until you answer that fundamental question, relative to what?
And that leaves us with one last, kind of mind-blowing thought to chew on. We know the Earth moves relative to the Sun, and we know our Sun is orbiting the center of our Milky Way galaxy, and our entire galaxy is hurtling through space relative to other galaxies. So, what is the whole universe moving relative to? Now that is a question for another time.